It is my pleasure to introduce Klaus Gessner, Chief Geoscientist. Klaus is a strong advocate of integrating geoscience data sets to better understand the geology, and his talk will take us on a journey through the western Yilgarn Craton.
Okay, let's get straight into it. As we've heard from Simon before, lithospheric architecture is really one of the key things to understand mineral systems. This has been, been part of many studies, and we know that. And it's the scale of the craton and the state that we are good at collecting data, and this is really what drives a lot of our initiatives, particularly in the Yilgarn Craton. So what can we contribute to that? Well, we acquire large-scale pre-competitive data sets, just like the passive seismic, the MT, the active source reflection surveys, and also, very important, the geochemical and isotopic mapping initiatives and the geochronology we collect. So we then provide relevance and context. We integrate these in the framework of geological processes because ore deposits don't form in a vacuum. They are a byproduct of crustal evolution and reworking, particularly in the Archean, where a lot of the continental crust is formed, and there's a really high endowment of mineral deposits. And then so we add our knowledge and our experience to produce from the information knowledge products. And so today we'll be focusing on how the geochemistry and the seismic methods can help define and interpret large-scale structures in the Yilgarn Craton. So one of the most successful things we've done over the last few years, and a big shout out to Hugh and his team, and to Alicia and Jack, has been the geochemical barcoding or chemical fingerprinting, and another shout out, we've actually been able to be shortlisted to the WA Premier Science Awards. That'll be for next week. So if you haven't voted on this, if you don't know, go to WA Premier Science Awards and put in your vote for that. That's a great achievement. So one of the outcomes of this has been to the identification of east-northeast trending compositional domains in the Yilgarn Craton. We published this 2 years ago in geology, and so the interpretation is a bit tricky. It can be interpreted as a deeper source for the granitic and felsic rocks that have been sampled and analyzed, but it could also be an area that's more fertile and has more water in the source. But the interesting thing here really is that these northeast domains, they continue across the traditionally mapped north-northwest trending terrain boundaries, and that have been largely identified or interpreted from potential field, and that includes also part of the eastern goldfields, and that's really interesting in that regard. And it was a bit of a surprise, but we've been looking at this data for a while, and we keep finding evidence for that. I mean, there's also, if you twinkle, there's also something like a compartmentalization of gold mineralization across the Craton, and well into the eastern goldfields. So and there are some large-scale gravity signatures that you could convince yourself show a similar thing. Well, one of the interesting things here is that the geophysics, some of the geophysical surveys we've done have confirmed this. So the first slide I'm showing here on this is from a paper that will come out next week, maybe. So this is part of an ARC linkage with ANU, between ANU, GSWA, GA, and the Department of Fire and Emergency Services, where we combine deep seismic imaging with earthquake hazard studies. But what you can see here on the right-hand side of the map is shear wave velocity at a depth of 28 kilometers in the crust, and it shows a similar kind of east-northeast trend that hints at a higher velocity, possibly a more mafic lower crust in this region. Of course, also our own WA array has produced data recently that backs this up. The crustal thickness map you can see in the center also shows this trend, as does the plot on the right-hand side, which is VP-VS ratio. And what that means is that the higher the VP-VS ratio, so the pressure wave versus the shear wave velocity, that means the higher this is, the more kind of mafic the crust is, and it's integrated over the whole thickness of the crust, not just a particular layer. So that's really interesting, but how, what does that really mean? But in a more detailed view, I'd like you to look at these two cross-sections. The upper one goes through the you and me terrain, and the other one is through the corrosion tectonic zone of in the southwest. So both of them, again, are shear wave velocity, so they give you a hint on how fast and how dense the material is. And you can see that what I'd like you to take away from that is that even though they're supposed to be terrains that have a similar tectonic history, they're actually quite fragmented along strike. So there's a huge along strike variation in the structure of those terrains. What does it mean? And why is that? That's a good question. And one hint is that there's a depth dependence to that. So again, the same paper referred to before by Ping Zhang from ANU that shows us different depth slices through the velocity structure of the southwest Yilgarn. At 4 kilometers depth, you can clearly see the slow sedimentary rocks of the Perth Basin, but you also see a northwest trend in the Yilgarn Craton. If you go further down, something very strange happened. We now see a high velocity zone east of the Darling Fault within the Yilgarn Craton. Really don't know at this stage what this means. But then if you go down deeper, as you've seen before, we see 28 kilometers depth, that east-northeast trend developing. So there's a clear change in structure in the cratonic crust with depth. The next thing I'd like to show you is what looks like a very average image of a seismic reflection profile. It's the Southwest 1 line we are currently interpreting. And the reason why it looks so faint is because I will show you some other structure, some other visualization of this. We have worked with, over the last few years, with Andy Calvert, who's an expert in Archean hard rock seismic in Vancouver. And because seismic profiles today are usually acquired over bendy roads, it's possible to use the curvature of the roads to triangulate the reflectors, so you can kind of assign a strike and a dip to the reflectors themselves. So it gives you a way of mapping the strike. And all you need to know from this image here is that green comes across reasonably well. Green is in the lower crust, and that's a strike of about 60 to 70, so that's east-northeast trending, whereas the purple ones, the purple reflectors, are more in the north-northwest orientation. And so basically you can see here that you have a north-northwest dominant reflectors in the upper crust, and east-southeast reflectors are dominant in the lower crust, so clear layering there as well. And a similar thing we can see with some of our own seismic lines we've acquired in 2019 in the Eastern Goldfields. This is one example across Campbelda. You can see the structures over here, and then in the same type of analysis, you can also see that the lower crust and sort of the background is more east-northeast, should be east-northeast, not east-southeast, sorry. Dominant versus the structures that cut the system are more north-northwest dominant. They're the typical structures that we know are fertile and control a lot of the structure in the Eastern Goldfields. Okay, so what does it mean? Well, we think that there's a number of primary structures that exist in the Yilgarn Craton. They could be things like the Murchison Rift, the southern high strontium over yttrium zone. They are long wavelength compositional variations, but what they are, we don't know. Are they arcs? Are they rifts? At this stage, very difficult to know, but we will be looking into this. And then we have secondary structures. They kind of control where the greenstone basins form, and they form at a high angle to the primary structures. And they also preferentially reactivate during crust shortening. Then we have structures that define the Paleoproterozoic passive margins of the Yilgarn Craton. And interestingly, they are parallel to the older structures. So at that stage, we have failure of the entire crust. We form passive margins, and for some reason, they form where these large-scale compositional domains are oriented. So one of the questions one asked is, are these structures, do they form at the same time? Are they composite, or are they sequential? Yeah, it's not. That's an open question, I think. It could be something that goes back to a segmented rift structure or a rift transform geometry. And one could also ask the question, how are they related to the granite domes and greenstone basins we see in the eastern goldfields? So I think all of these are open questions, and I cannot answer any of them, but I think they point us to a very, very interesting problem. So basically, the Yilgarn Craton shows compositional variation at different scales and depths. We have identified a set of primary east-east trends that are deeper in cross-section and wider in the map, and secondary structures that are shallower and narrower. How does that form, for instance, things like the Kalgoorlie Rift? Well, it could be things like movement along the primary trends may have resulted in a segmented rift, just as shown here for models of opening of oceans. And in that case, there's no such thing really as a coherent Norseman-Wiluna belt, but it could be an array of pull-apart rift basins. There's also a lot of data, particularly that was collected in the 90s, that suggests that there's a lot of stretching parallel to the trend, and that could be due to transtension while this was opening. But be careful, because there's not much outcrop. There's some drill core, and there are multiple options for activation and reactivation in successive extension and shortening events. And that's all. Thanks.